Good afternoon, everyone, and thanks once again to join a session on robotics development workflow with MATLAB and Simulink. So, in this session, basically, we will see what is the workflow of robotics development with MATLAB and Simulink. So, because lots of expertise requires to design a complete robotic system. So, this session will be kind of broadcast session. We will see what kind of modules will be required. Lots of modules are available which we can use to design a complete robotic system. This will be our agenda in this session: introduction, advanced robotic system, robotics development workflow with MATLAB and Simulink, and some key takeaway that what we'll get after the session. And we'll start from the application. So this, you see there, this is a chess player robot, right? So this robot is completely designed in the programming which are done, that is in the MATLAB, and it is deployed here. You see that here the camera is also installed, if you see in here in this area, right? So computer vision is also used, and apart from that, if you see, this manipulator is also added and is playing this. Is the complete programming is done. So before that we'll discuss also that what kind of robots we can design. That's very important. And once we get that, okay, what various kind of robots are there, then you can go for the designing of dynamics of the robot, kinematics of the robots, and further if you want to interface with ROS, robot operating system, that things also possible, and we'll discuss how we can use MATLAB for all this mechanics and this applications to design the robotics applications. You see that these are some types of robots. If I'm talking about the core robots can be manipulators. Manipulators means something a robot is taking some things and putting somewhere else, like this one which you see, this first diagram here, this one. So that is a manipulator, just a robot arm if I have to design it. Or mobile robots. Mobile means automated kind of thing. So this figure which you see, that is a mobile robot. We are not controlling this itself. It's this robot is doing its own task and it is moving. That's mobile. That's why it is called mobile robots, right? Or humanoid robots. So everyone is aware. Sophia, right? Sophia is the first citizen of the Saudi Arabia, right? So this is a humanoid robot. So means a replica of the human. If you have to design that are called humanoid robot. Or UAV, unmanned kind of devices, vehicles, like drone is the example of UAV. So we have a special toolbox, UAV toolbox, to do analysis on that. Okay, autonomous robots. The big example of autonomous is robots is automated driving system. So lots of ways are there, lots of expertise we require, lots of modules we require, that how we are going to design a complete robot. Even nowadays people use machine and deep learning. Without AI, without machine and deep learning, designing a robot is incomplete. Some more applications. Precise is actually a surgical. They develop a surgical instruments, right? So they use MATLAB to design a robot, world first eye surgery robot using model based design. Model based design means they use the Simulink to design that. The challenge was that develop a real time control system for robot assistant surgical procedures performed within the human eye. So that's the eye surgical. This is the world first eye surgical robot using the. They use the model based design there. So solution, they use the model based design with MATLAB and Simulink to model and simulate the control system, and use we saw already how to design a control system, right? They use the Simulink coder and Simulink real time to deploy it to a real time target. So Simulink coder is used to generate C++ code from the Simulink. So once they developed a robot on Simulink, and after testing they deployed that model in a hardware also, means the controller part, how that robot will be controlled. So the result was core controller developed by one engineer, patent safety assured road map to industrialization. So it is patent right now. Mr. Martin Belen, who was working with this project, as he said that MATLAB and Simulink provided a single platform that supported our complete workflow and all the elements and protocols we needed for our robotic system that enabled us to quickly develop a safe, in a short duration. MATLAB is the way, Simulink is the way that in the short duration, I mean, we can develop any kind of system. So they developed a safe real-time device ready for clinical investigation. Some other applications, Mitsubishi, they actually designed a robotic arm for removing nuclear fuel debris. So robotic arm is a example of manipulator, right? So challenge, design a multi-axis robot, means it can move anywhere as I want, something like that. Design a multi-axis robot for removing molten fuel debris from the Fukushima Daiichi nuclear power station. And solution, they use again MATLAB and Simulink to perform hardware measurement tests and to model and simulate the individual robot access and controller. So they did design the mechanics part of that also. They designed the robot dynamics also. To control that robot, they use the controllers. The lots of controllers libraries are available in MATLAB. So Mr. Tadashi Murata, he was a part of that project. As I said, model-based design with MATLAB and Simulink supports a wide range of options from classic to modern control, which made it possible to respond easily to any changes in design constraints and to meet the demanding accuracy requirement for this robot. So as in MATLAB, if I am talking about MATLAB functions, MATLAB libraries, thousand of times they are tested, so you need not to worry about accuracy of the functions, accuracy of the libraries which are available in Simulink. Just design it, test it, like we have done in the previous session in the controller, that okay, I want this speed from motor, then how to validate that with the controller, and further we use some kind of tuning kind of things also, auto tuner and all these things, how to tune that PID and all that controller, right? Some other applications, that's from Airnamics. They develop a unmanned aerial system, that is the UAV which I was talking about, for close range filming with model based design. So again they use the model design. So whenever the robot world is coming, they are using the model base. By model base is used to design the system virtually, design a digital twin also. We'll discuss little bit what is digital twin. Once you have designed, there are different ways you can test your models, using software in the loop, processor in the loop, deploying the controller in the controller, that is processor in the loop, hardware in the loop, means you are testing with the real hardwares also. So three engineers were there. They designed this complete unmanned aerial system. So they again use the model-based design and MATLAB and Simulink to accelerate the design. So we have options in Simulink to accelerate our models. Debugging options are available, and the implementation of the vehicles fly-by-wire and flight management system software. They interface with the flight management system software as well, and the result, time to market shortened by up to an order of magnitude. Test flight anomalies quickly resolved. Anomalies means some sudden changes if happen in that robot, or some kind of fault detection kind of things can occur, right? So that kind of testing they have done. And Mr. Marco, as he told that with border-based design or three engineer team, only three engineers were there in that team, found more than 95% of control software bugs before the first flight. We use the test flights to increase our Simulink models fidelity and isolate remaining bugs with the high precision. So in MATLAB, it's not only you are going to test it, we have a different license available in MathWorks from MathWorks to test the bugs there from the code which is generated, like polyspace bug coder is there, polyspace bug finder prover is there. We can use polyspace and test that if there are some kind of bugs available or not. And then this last one which I am showing you, Krones, they develop a package handling robot using digital twin. So what is a digital twin? Let's say that I have a real plant, and if I what I want to do, I want to make a replica of the real plant virtually in the Simulink. Why we require to design a virtually if I have a original real plant? To because on real, if you have a real plant, real time plant in the real world, it's not possible to do analysis directly on the real time plants. So once we have a replica of that in the Simulink, you can predict the future behavior of the system, right? You can predict you can do some kind of predictive kind of things also, if you have to take some decisions that how your system is going to behave in the future, or what kind of component is going to stop. So in digital twin, first thing is that we designed a replica of the real-time plant, and once it is designed, we use the sensors and we log the real-time data from the original plant, and we use that sensor data in the Simulink. We apply on that digital twin model to check the behavior of the system. Or let's say if I have to design the controller for my real-time plant, means the output which I want, if I am not getting, again we can design the virtually in Simulink, and we can design some kind of controller and we can apply on the virtual plant. When we are happy with that, then we can apply with the real plant using the hardware in the loop, right? So the challenge was that increase the performance of an automated beverage packaging system by incorporating a dynamic tripod robot into the design. So this is a tripod robot solution they use against Simulink and Simscape Multibody. So we are going to discuss more detail what is Simscape Multibody. They use the Simscape Multibody to create an accurate digital twin, means accurate replica of the real-time plot that supports design optimization, faulty testing. As I was telling that if in future maybe some component is going to stop or some faulty data will come, so they create some kind of forecasting model on the virtual plant to predict that okay, what will the behavior in the future, if there is some kind of fault or not will happen in the future or not. So they use the optimization to optimize that. They use faulty testing. For the faulty testing, they use the predictive maintenance. There is a one special toolbox in MATLAB that is called predictive maintenance to identify the fault from the system. And the result was robot performance increase, product development time shortened, the development of their products. Any industry, any manufacturing company want that their product development time will be decreased, right? Testing time significantly reduced. Simulations of the digital twin in Simulink enable us to obtain data and insights that would be either impossible to give by a hardware test or simply too costly and time consuming, right? If you're doing this traditional way, then it will be a time consuming. Why time consuming? Let's say if you have to design a simple controller using the C++, lots of lines, lots of codes will be required, and it will take months to design a single controller. Why not to design in the Simulink? Already ready-made controllers are there, and further we can generate the embedded code from there, right? Visualizing forces and movements help to us understand the effects of individual components. So as I told, when we design the model in the Simulink, at any point we can measure the input and output from them. Outputs, if I have to, whatever the data if I have to measure, I can measure and I can do further analysis. Okay, if I have to measure the force, if I have to measure the torque, if I have to measure the velocity, that what velocity is there at every point, whatever the robotic model I have designed, we can measure all that things. So whatever we saw that application in the previous slides, what challenges will be to design a robotic system, because different kind of robots are there. Applying multi-domain expertise, complexity of algorithm, end-to-end workflows, means from the designing to the till the manufacturing, manufacturing and then selling also. Means from end to end, deploying, from the designing, testing, deploying and launching commercially, end to end workflows from that. This kind of challenges, and we'll discuss how this kind of challenges can be overcome using MATLAB and Simulink. Okay. So now let's discuss about the toolboxes which you will be required. Some toolboxes, there are more than that you will be required. Depends what kind of robot are you going to design. So first of all, we require a control. Sense means for the perceive we require some sensors, planning, connection. So for the control, like we just saw in the previous session, control system toolbox is there, predictive control toolbox is available there, and robust control toolbox is there. You can use it. We can use the Simscape toolbox to design an actuator which will be responsible to move the robot. Simulink real time to interface with the hardware. Okay. To interface the hardware, we can install the hardware support packages that is freely available. We saw acquire the sensor data from robots. We can use data acquisition toolbox to sense the data. Hardware support packages where sensors are installed, we can install, then we can acquire the data. Perceive means if I am designing the robot, how the robot will get going to take the decision, how the robot is going to take the decision. So robot requires to perceive means what is in front of the robot. If I'm talking about automated driving system, so I have to perceive first, okay, this is the road, this is the car, this is the building, this is that. So once I perceive that things, I will be able to take the decision. Means robot will be able to take the decisions, right? So we can use computer vision, we can use robotics toolbox, we can use phase array system, states and machine learning. Planning, okay, for the planning also we can use robotics toolbox. We can use state flow. State flow is used a good way to plan something like let's say after some duration I want to start some my component, and after some durations, after some threshold value, I want to start another component or something like that. Okay, so we'll see what is the state flow also in MATLAB. We will discuss about that also. So robotics toolbox is also there. For the communication we can use ROS. This is the open source robot operating system. So this is freeware. You can install that ROS. We will later discuss what is ROS, and it is a freeware. Basically, it is a set of programs. It is not a operating kind of system. It is a set of programs which allow to connect with the actual robots from the programming language with the robot. Okay. For the communication, let's say if you have to design UAV kind of systems, we can use communications toolbox in MATLAB. We can use WLAN system toolbox as well. So apart from that, there are some other 5G toolboxes there. Let's say if I have to connect, I want to use IoT also. So we can use 5G toolbox for the analysis and for the high speed, because IoT require a high speed. So we can do analysis on 5G also. We can design our 5G systems. Let's discuss about the workflow of this robot. Let's say that I have to design a walking robot. What workflow will be there, and how we are going to design in MATLAB, what modules will be required for that to design this walking robot. Okay. So once I am happy with that, then I can go for the hardware implementation, right? So how to animate and how to design all these tasks, we are going to discuss all the modules which will be required for that. First of all, once you design the robot which you are going to design, we require a robot model and control model. So two subsystems are there which we require. Okay, in robot models, we require to design a robot mechanics. We will discuss what is robot mechanics as well, and actuator dynamics. This will be used to control the robot. Okay, once we have this mechanics and actuator dynamics, we require some controller model to control this, and based on the motion planning, that how my robot will move in this case. Okay, so we will have some reference output like we saw in the controller part, and this will be the controller which will control this actuator, and this actuator will be responsible to move the robot. This is the complete robotic system if I am talking about this walking robot. Okay, let's start. So how to design a robot mechanics in MATLAB? So two options are there. You can build from scratch or you can import from CAD model. So your idea is you can use to import the humanoid kind of models. If you have mechanics, I mean chassis of the robots or mechanics of the robot from other software like CAD model, we can import it, or in MATLAB we can design from the scratch. Okay. So if I have to build from scratch, these libraries are available. Different kind of bodies are available. Body geometries, inertias, color also if you want to change. Different frames are available. These libraries are available there. And these are the assembly libraries available there. How you are going to assemble that, how you are going to join that, connect bodies through joints, gears and constants. So this kind of libraries are available. Dynamics means from where you are going to provide the dynamics, force, or so your robots will have some kind of motions. So apply. So we have sense force, torques and motion libraries are available here to build from the scratch. Okay. So let me show you about Simscape Multibody here. Let me show you the first of all library, what libraries are available. So this is a part of physical modeling. So if when I am saying physical modeling, then we will go in Simscape, and Simscape this is part of a multibody. And here you see that we have belts, cables, body elements, constraints are available, curves and surfaces, forces and torques are available to provide the kinematics to robot, right? So if I scroll this more, if I go here, body frames, these are the variable mass body frames are available. Just we have to select, right click, add in the model, and we have to connect this. We'll see how to connect all this. So you see that curve and surfaces are there, force and torques are available here, joints are available. How you are going to join, either you are using 6 degree of freedom, bearing joint, bushing joint, Cartesian joint, different joints are available. How you are going to join, even not only that, welding joints are available, revolute joint is available, spherical joint is available, different joints are available. Okay, let me show you some basics of that. I'm just switching here. Let's say if I have to design a simple pendulum, if I am talking about, just I'm going to open that model. So you can use Simscape Multibody for the 3D simulation, 3D models, 3D robots, or mechatronics if you are working on mechatronics. Okay, now you see that the blocks which we have here, these blocks are already available. This is the world frame, how it is connected. This is a revolute joint, just you have to connect with the world frame, and this is the rigid transform, means how you are going to transform this, means where you are going to link this pendulum which I have. So when I double click on this, you will see here translation. So in plus x direction, minus x direction, or y direction, z direction, how are you going to connect? So there is the option here available, and this is the offset that total, let's say width is 4.5 centimeter. So I am going to connect just in the middle of that or something to divide by 2, right? And if I click here, and you see that if I have if I have to specify position, velocity, we can provide here an internal mechanics of this we can provide here. Apart from that, if I go in equation, And here torque, if you want to provide, you can just put on the torque, provide by the input or automatically computed. So it depends on you that if you want to provide torque also, right? And the motion automatically computed or provided by the input, how the motion will be computed. Sensing, if I want to measure the position of the this joint, just I will take that. Once I will take this here, I will get the option here to measure the position. So if I have to measure the position also of this robot, I mean this pendulum, just what will I do? I will just require a scope to visualize that. And one thing more here, this model which you see, this is a physical model. So physical, the signal will be bidirectional, right? So signal which is coming, if I have to visualize in this scope, because this is a Simulink block, so we require a converter from physical signal to Simulink converter. Okay, so that we are going to search here, that where it is. So this will be in the Simscape. Okay, in the utilities, there is a physical signal to Simulink converter. Otherwise it will be not able to connect directly. If I move, if I move this here, and if I want to connect this directly, this Simulink, because Simulink models are unidirectional, that's why you see that it's not connected, right? So what we can do, we can add this converter here. Okay, and further, so this is a benefit using this here in Simulink, that you can measure the forces or motion, velocity, displacement, all these things, right? And here I can visualize the motion of that also. So I am going to run for this 10 seconds. So these blocks are available in the library, and when I click on this block, here I can provide the inertia, dimension, width, height and thickness. We can provide in the same, if it is centimeter, then you can choose the units also. Type based on density, what will be the density of this block. Okay, so we can provide all this from here, and this is a mechanism configuration. So what will be the gravity? We are assuming that it is minus 9.8 meter per second square. So this is a mechanism configuration which we can provide it here. So once we connect, so this is the basic, this will be required, this you will be required, and this solver you will be required. So this solver to solve this physical system. So solver also you will get from here. Okay, so once we have all this, I am going to run for 10 seconds. So this is a pendulum which you see right now, and you see that it shows that how it is moving, right? So there is a different way to visualize. Just click on this. You see that now we are able to see this. I am going to run this again, how it's moving, and its coordinate shows here how it looks like, right? So different way. If I click on here in the four dimension, I can see that from the front, from the above, from the below, from all directions we can see here. This is simple pendulum. If I am talking about, you can more modify, you can change the color, you can add some kind of ball there, some, I mean spare, you can add it also there, depends on you. And if I click here, and you see that how this pendulum was moving to and fro with respect to time. So this is the position. So we can log this data for the further analysis as well, right? So this is the from the scratch. If I have to design, how we can design some advanced robots, if I have to design some automatic or autonomous system, so that is also possible. We require to connect multiple components there. So this is a suspension system. Let's say if I am working on automotive system, so if I run this, and these are the subsystems. When you go inside, again that blocks are used, which I showed you just there. It is testing the suspension of that, which you see here right now. So either you can design from the scratch, or you can import from the CAD model also. That's the perfect. The ball is its suspension is very perfect. If it was some distortion there, then this ball would be fallen down. That's why their ball is there, that to check that suspension is just going straight or not, the direction which I want. Okay, I'm going to close this and I'm going to stop this model. Now the next part is how to import. So two kind of models we can import. If I have URDF model, which is simply we can use sim import, or if I have if I have to export it, we can use CAD. CAD assembly or some models will export, we can use this. Otherwise we can use sim import for the import, and this will be used for the export. Let's say I want to integrate with other I mean, if I am working on a big project, then we can export that models as well, right? So that's very simple to do this task. Just 1 minute. What we require, just a model name and simple sim import commands. Once when I run this, what it will do, this is designed in the different platform. Okay, so once when we use the same import command, when you import this model here, it will be translated in the form of MATLAB. So you see that lots of blocks we require to design this model. Instead of using this, use any CAD model to design a chassis or mechanics of that. And you see when I run this, and will get the output in a 3D model. So it will take a little time because the complete robot, if I am talking about, this is the complete chassis. And what we can do once we import, we can provide some torque, some position, some velocity to control this model completely in the Simulink. Perfect. Okay, I am going to close this. I'm going to close this also. Just open the dock of sim import. Just wait a minute. Some spelling mistake is there. What was the function here? SM import, right? Here's the documents, and you can see what kind of file formats are supported for that. Okay. Here some examples will be also given. If I scroll here below, some examples. How if I have to import some. Let's say that I have one robot arm, and I want to import this in Simulink. I mean in MATLAB. Just I will use the sim import command, and this is the CAD model again. So again it is translating. It is translating in a Simulink environment. Once it is translated, you can execute that, and whatever you want to do modification, you can do a modification also from here. Okay, so this is the way how we can do. Now you see that this robot arm is uncontrolled. So once we import in the Simulink, we can design some kind of controller to control this arm, right? And we saw controller also how to do design a controller part there, right? Okay, this was about the mechanics of that robot mechanics. Either you can import from CAD model or you can build from the scratch. Fine. Next, okay, now about robot mechanics, internal mechanics, external mechanics. So two things are there. In internal mechanics, every joint blocks, that is it can be a translational or rotational mechanics. Internal in the models can be assigned mechanical stiffness, damping, or some initial conditions. External mechanics, first you can set up the direction and magnitude of the gravity. Equally important for leg robots. If I am designing the leg robot, that robot which I was showing you, you need to model contact with the ground. So two kind of mechanics are there, internal or external mechanism, because external forces you are giving to that to make the motion. Internal mechanism means you are calculating the parameters of the joints of the robots. Okay, now about actuator dynamics and control. So we already know, let's say that I have revolute joint and I want some desired output from here. We can use simply like this PID controller here. We can add it and we can give some reference there. Means I want that based on the reference, this revolute joint will give me a output. So I can use controllers to control this actuator dynamics. Now how to design an actuator? If we are talking, we can use Simscape. So this which you see here, this one, this is a actuator which I am talking about. So Simscape models, how to design the Simscape model? Very simple model. I will show you how to design a Simscape model, how to use the Simscape, and what basic elements will be required to design that. So you see in this actuator, this motor again which we saw in the previous session, this motor is there to design, and this part are the controllers for that, how this motor should be controlled. Or instead of this, you can use PI or PID controller also to control this, right? So let me switch here. If you are working on physical modeling, first of all, just start from the Simulink. Okay, we require some basic components. So if you don't know what basic components required, don't start from the blank model. Okay, any model, if you want to design from the Simulink, that is energy signal bidirectional or some basic components, just start from the here. If you are working on electrical, use from here. Somebody is from electrical, working on electrical three-phase models, you can choose from here. Somebody is working on gaseous model, hydraulic model, choose from here. So I am just starting from the generic Simscape. Okay, so the basic components which I required, I have here. Simulink to physical converter is there, physical to Simulink converter is there. Let's say that I am going to design a half wave rectifier, or you can design the full wave also. Let's say I am going to design a half wave rectifier, a very simple model I am going to design. So simply I will go in the library, I will go in the foundations, in the part of the Simscape, and this is part of electrical. To design a half wave rectifier, we require a diode. Just simply I will add it. We require a electrical difference for that. Just we can choose it from here, and you can add the transformer also if you want. So we have a diode, we have a electrical difference, we require a resistance. So inductor is also available. Maybe if you are going to design some kind of filters or different kind of things, you can choose the inductor also. Okay, so I am going to choose the resistance from here. Okay, we have some components available now to sense from there. So for the sensor, what we are going to sense, current sensor or voltage sensor. So let's say that we are going to measure the voltage sensor from there. So voltage will be added parallelly. If I have to measure the current, then we will use current sensor, it will be added serially, right? Let me switch, and later we will see what more component will be required here. So this is the basic elements which we require. So I am going to rotate this resistance, and I have this sensor, I have this diode. Just simply I am going to connect this here. Also we require a voltage, right? So I am going in the library and I am going in sources. So I have a AC current source, AC voltage source, controlled current source, controlled voltage. So different sources are available. I am going to choose controlled voltage source. I am going to control this from external signal. Okay. So here I have this. I am going to connect from external signal. Again I am saying, and further I am going to connect this here, and we require a ground. Just simply I am going to connect this here. Okay, now I want to measure the voltage across this resistance. Just simply I will double click on this. Let me double click on this. Let's say that the resistance is 100 ohm. There are different units you can select from here. Just I'm going to apply this, and now I have to measure the voltage. So here is the option plus and minus sign. So plus one I am going to add it here, and this minus sign I am going to add here. Now I have to measure voltage here, so we require a physical to Simulink converter, that is already we have, and here I am going to connect this. So this color which you see here, this black one, black shows that this is a Simulink part. The blue which you see, that is a part of electrical. The green which you see, that is a part, that are libraries of mechanical. Okay, now I am going to control from external source. Let's say that I am going to use the sine wave from the Simulink. I am not going to choose this voltage source, this AC voltage source. I am going to choose from the sine wave because I am going to use the external signal. So let's say I am going to add it here, and simply I am going to connect it here. Sorry, it will be not connected, so I will connect first here Simulink to physical signal converter. Okay, once we have done this, just I will click on this. Here I can mention what amplitude I want and what will be the frequency. Let's say it is 50 hertz. After providing everything, just simply I am going to run for a small time because it will take a lot of time to execute. So, and for 0.1 second I am going to run, and further one thing more we have to do, we have to choose the solver. Because this is a physical signal modeling, so we require a different kind of solvers to change that. Okay, so I will go in the modeling, I will go in the setting. So if you are modeling the physical signals, always choose solver from here. If you have simple basic Simscape model, choose this. Some special technology if you are using to design electronics or electrical system, you choose this one. So I am going to choose this one, and I am going to check on this solver. I am going to apply, and I am going to run this for 0.1 second. Okay, one thing we forgot to add, MATLAB is giving us error, this solver configuration, because overall this will be converted as some kind of algebraic equation, algebraic differential equation. To solve this, we require this solver configuration, and you can connect this anywhere. So once we have done this, just simply I am going to click on this, and you see this is for 0.1 second. Let me increase this. Let's say I want for 0.5 seconds, and again I am going to run this, and you see that perfect, it is connected as a half wave rectifier. So you see that some distortions are here, right? Discrete kind of things. So what we can do in that case, I will go in the setting. Step size is configured automatically from MATLAB. What I am going to do, maximum step size I am going to give 0.01 second. So the if I give 0.01 second, means number of elements, number of samples will increase, so it will look like continuous. It's not, we have to decrease that more, so I am not going to do, but you can decrease that so it will looks like a continuous. Okay, so this basic things which I wanted to show you, if you are working on mechatronics or multibody, we require this, and these are the sensors which you are going to measure. Okay, one thing more I wanted to show here, just let me switch in the Simulink, sorry, in this help and in Simscape part. Here you can learn that what are the essential steps to design a physical model. Everything is given, like if you have to design this mechanical system, spring damper system. So step by step here process are given. You can go through that and you will have an idea how to design that kind of things. Okay, and how Simscape models represent physical system. Here is the options of here how Simscape model works. Here it is given, and how Simscape models, how Simscape simulation work, That's also step process is given. So before designing any kind of robotics or mechatronics, is go through that. Okay, fine. Okay, I am going to close this. Now I'm switching here. So this was about the actuator, how you are going to design a actuator dynamics. Then how are you going to control that by using the controller. Okay. Next, motion planning. So once we have designed the robot design, so you require to find out what will be the optimal geometry, size, position, cross section, whatever parameters you require, and dynamics of that, like mass, stiffness, damping, equivalents in electrical or fluid actuators. If you are using electrical or fluids, and let's say I don't want to use electrical, I want to use fluid to actuate my robots. Then once we have designed the control system, then we do a motion planning, finding a sequence of motion inputs that satisfy overall planning goals. The last one is that's the motion planning. Okay, for the motion planning, we require to train our robot that how it will move, how it will behave. So two ways we can train that: closed loop and open loop. Closed loop we saw in the control system. How we are going to train it? Let's say if we have to design this here, in this case this is the open loop, and genetic algorithm from global optimization is used to train this robot. So two things again. Are you going to use the closed loop or open loop? Okay. So if you are going to choose closed loop, in closed loop you can use controllers like PID controllers, which we have used just before one, or you can use some advanced algorithm from deep learning, reinforcement learning. So reinforcement learning is a self-learning kind of things. We'll discuss later what is the reinforcement learning. If I have to train that this robot will learn itself, how we can do this task using reinforcement learning or deep learning or machine learning also you can use. But if I am going to train this robot as an open loop, we can use optimization kind of things to optimize this, or we can add some compensator also there. Okay. So about the Simscape, we saw what is Simscape. Simscape, sorry, whatever we saw, Simscape enables you to rapidly create models of physical systems within the Simulink environment. We saw already Simscape. Physical components models based on physical connections that directly integrate with the block diagrams and other modeling paradigm. Your model systems such as electric motors, breeze rectifiers, hydraulic actuators, and refrigeration system by assembling fundamental components into a schematic. So in a schematic way, we connect everything. Then further write the parameters value. We execute this. If a system is not giving the output which we want, then further we apply some kind of controllers. So in Simscape, have libraries for drive line, for mechanical modeling, for motor modeling, for vehicle modeling, electrical system we can use to design a battery part of that. Let's say if I have to design the battery, or let's say if I have to design the motor actuator, we can use electrical systems. Or if you want to design your actuator using fluids, you can use fluid libraries from there. And multibody is used to design the mechanics of that, means a 3D model of that, as well as chassis also of that robots. So Simscape Multibody provides a multi-body simulation environment for 3D mechanical systems such as robots, vehicle suspensions, construction equipment. Like if I have to design a crane, then we can use Simscape Multibody to design a complete crane system. Aircraft landing gear, let's say if I have to design, or model multi-body systems using block representation bodies, joints, constraints, force, elements, and sensors. Apart from that, if you have a multi-body, you can import complete CAD assemblies including all masses, inertias, joints, everything will be imported. It will be translated in the form of Simulink way to do this kind of things. Okay. Now, MATLAB makes machine learning easy and accessible. So if I'm designing a closed loop kind of robots to control my actuators, we can use traditional machine learning or we can use deep learning also. So very widely machine and deep learning are used to design the robot. That's why I included this topic as well. So let's say how traditional machine learning works. Let's say that I have to predict different kind of animals from here, from these images. Let's say this is a perception of means what is available in front of the robot. So it can do some kind of perception and then further robot can take decision on that. Okay. So in traditional machine learning, I have multiple images of animals and I have to classify that. So we require to extract the features. Let's say that as a human, if you see a dog, you can say okay, this is a dog, you can say this is a cat, this is a lion, this is a rabbit. Why you are able to say that? Because already you have extracted features and that features are saved in your mind. Means there are some kind of unique features of dog and cat. That's why you are able to say that this is a dog and this is a cat, right? So in traditional machine learning, we require to extract the unique features. That features we provide to the machine learning model, and machine learning will learn itself and it will start predicting, okay, this is a dog, this is a boy, or this is a bicycle, or different animals are there, so it can say this is a dog, this is a lion, this is a cat, right? In deep learning approach, this is end-to-end learning. So in this case, we don't require a handcrafted feature. Means we don't have to extract the features manually. This deep learning will do this task automatically for us. So why I am showing these things? Because that walking robot which we are discussing, these are the workflow. I mean, depends on you. Either you are going for the closed loop, open loop and mechanics, what modules will be required from MATLAB, you can use that. So for the traditional machine learning, you can use statistics and machine learning toolbox. And for deep learning, there is a deep learning toolbox. Previously it was named as neural network toolbox. Now it is named as deep learning toolbox. And accuracy of deep learning is higher than human from 2015. We can be wrong, but deep learning will be more accurate than human as well to predict. Okay, now next, car as an advanced robotic system. So till now we discussed what kind of modules we require to design. Some more advanced modules we are going to discuss in MATLAB. Let's say that if I have to design a car as an advanced robotic system, is self-driving car, automated driving system. Okay. So there are some certain things which we require to do that: planning, localization, global mapping. That is this complete. This is a perception and based on the plan. Motion control, how we are going to control this autonomous system. Obstacle avoidance, if in front of the car there are some vehicles, some bicyclists, something, then how it will avoid, how it will take the decisions. So this perception and planning we require. And for perception we can use lidar to identify the distance, that what the things which are available in front of the car. Let's say it is a truck or it is a some other cars, what is the distance between them and what is the speed of the car. Based on that, this car will take a brake automatically. We can use camera, we can use radar also, or we can use some sensors also for the tracking purpose, GPS, like global positioning system and all these things. Okay, so one part I am going to show you. I will not execute that, but it will take long time. That's why, let's say that I have to design this perceive part which I am talking about. So this car, or maybe instead of robot, it will be how it can perceive that what is available in front of that. So first of all, we will discuss about capabilities of an autonomous system, autonomous robotic system. First, we require to sense. So we require a different kind of sensors. It can be a vision sensors, it can be a lidar sensors, or some other kind of sensors to sense that what is available in front of the car. Once we have, we perceive that okay, this is a pedestrian, this is the car, this is the road, and this is this and this is that. After perception, we take decision that okay, if this is a car, distance is this, should I have to take the brake or not, and what will be the acceleration based on that, all these things. And what is the benefit of automated driving car? Fuel consumption will be less, because it will predict that okay, this car is going with this speed, and how much brake I have to take, how much acceleration I have to take, everything will be automatic, right? So sense, perceive, and decide and take the plan based on that. And then so once you plan that, then act that how you are going to act. And all these things you can design in a single hardware. And you see, this is a video which is taken, that is an automated driving system which you see right now. We are going to talk about this part here, this one, okay, in the next slides. So why deep learning for robotic automatic driving system? Complex perception tasks, lots of things are required which we require to identify, like what is the drivable area, what are the lanes, what are the other road markings, traffic lights, signs, everything through a single algorithm we can do using the deep learning. Okay, other road users, vehicles, pedestrians, cyclists, in a single deep learning model we can track everything. Okay, so hard to develop this kind of things from traditional algorithm, not possible. Traditional algorithms, if you are using mathematical equations, you are using, it will take years to design the complete this perceived things, right? So in deep learning tasks, what we can do, we can classify that, okay, classification, we can say okay, this is a highway scene, this is car, and this is truck, and all these things. Next part will be regression. Okay, where I have to drive in this lane or in this lane or in this lane, what is the distance between this both lane, right? That's the regression part, numeric values. Then once we have done that, then detection, that okay, this is a car I have detected, right? This kind of applications we can design using a deep learning. Now semantic segmentation, that based on the pixel intensity value we can do a segmentation. We can just annotate like this is the green, the blue one is showing the car, this color is showing the road, this is showing some flyover, this green areas. How we can do all these things in using MATLAB? To label our data, first of all, before training we require to label our data. So like we can label, here you see in this example, we can label this is the pedestrian, this is the car, this is the stop light, right? So how to label this data? In MATLAB app is available, ground truth labeler. Let me show you that app which is available here. So if I go in the app, and here you see that if I go here more, scroll below, and here you see ground truth labeler is there available, right? And let me show you how to label the images here. If I have to design some kind of autonomous robots for the perception, so I am going to switch, just wait a minute. Okay, no, it's not here. What I'm going to do here, I'm going in the app. From here, simply I will go in image processing. Just I'm going to open the video labeler. So instead of labeling everything manually, we can use these labelers to label that. Once it is labeled, once we have the ground truth data, we can use deep learning to train that kind of such models. So this is a video, so you can use multiple images or you can label the complete video as well. So here we have a image sequence. Just I'm going to select the image sequence, and this is the folder where I have all images. So I'm just not going to select everything. Let's say I'm going to select screwdriver, and simply I'm going to load this. And in this app all images will be loaded here, and there is the option to label everything. Like you see that there is a one screwdriver available. Just I will click here label. I will give the label name my label, and here you see that there are options: pixel label, semantic segmentation, which I was talking about here. If I go in the back, this kind of much deep learning, if I want to use semantic segmentation, pixel based labeling, that is also possible, and later we'll see one demo there on that. Let's say I'm going to use rectangle based labeling. Just I will select this and I will switch here. Okay, just I will select here, and there is option for sub labels also, so you can choose sub labeling also. There's a different option sub label here, labeling and sub labeling here. These options are available. And just start the labeling like this. Yeah, you can increase that. This is a screwdriver, something like that. And now further you can move like this. Some other images. This is the same images, actually here it is given there. There can be a different kind of images, and you can label it and you can give the different label names. Once you have done this, there is an option you can select the different algorithms, point tracker. If I have to label the pedestrian, we can use people detector. If I are working on vehicle autonomous system, we can use this. Once I have labeled everything, and I can export this data to workspace or in the file, and once I export this, we can use that data for deep learning training. Okay, fine. So next, okay, next, if let's say that I don't want to use deep learning from scratch, already world-class pre-trained models are available there. Like Inception V3, ResNet 50 is very good for medical images, VGG16, AlexNet, where 1 million images are trained with 1000 classes. Okay, so this kind of, or if you have any deep learning model from open source, you can use this kind of converters. You can use if models are from cafe, we have option available to import this kind of models. These are kind of transfer learning, means you are going to use pre-trained model for your data, because pre-trained models are already optimized, parameters are already optimized, and you are going to use for your data. If you are going to design from the scratch, so in MATLAB we can use this kind of apps to design the different kind of layers, like image input layer, what will be the image size, what will be the filter size, that's a convolutional neural network, then for the normalizations, and you can use this app to design a complete deep learning model without writing a single code. Okay, and the MATLAB, from the MATLAB code, once you have designed your code, you can generate the code for the CUDA or C++, and you can deploy on a hardware. Either you have a ARM or you have a GPU or if you have an Intel processor for the real-time application in real-time world. Okay, so MATLAB deep learning work like they access the data, design and train the data, and train on the GPU, it is supported, and deploy in a hardware. And further, if you want, you can optimize that also. So before that, let me show you how we do this kind of processing. Just I will take 1 or 2 minutes only. From here, just open. Let me open that folder where I have that model. So here you see I have that data available here. Here, these are the images, right? and
Sir,
here we have labels images available there, so we can use that app to create this kind of label images. It's
sir,
opening. Yes, please.
your screen is not visual, sir.
Am I not audible?
Screen are not visual, sir.
Screen is not visible.
Yes, sir.
Akhilesh, yeah, right now you're not presenting.
It shows resume your presentation. Resume. How it happened suddenly?
Yeah, now it's okay.
Okay, sir. Fine, fine. I don't know how it happened. So,
It happens accidentally,
yeah,
not
yeah.
an issue.
So here I was showing you semantic segmentation. Let's say if I have designed an automated robotic vehicle. So first of all, we require. I am talking about perceived kind of application of that. So this was the original image, and we have segmented based on the pixel that this color is cars, this colors are buildings, and this color we choose. These are the roads. And I showed you the app. We can use that app to label based on the pixels. Okay, just here we have the original image was like this, so we require the original image and the label one image. So if I have to label this image, let's say that I have to label that, I'm going to show you how to do a pixel based labeling. So from here, this is a part of image processing. I'm going to use image labeler, and a single image I will show you from here. Load, add images from the folder. Just I'm going to select some images from here. Let's say this one, two images, and I'm going to open that. So here you see, and simply first of all we have to create the label. You can, let's say that first label is vehicle. Just simply I will type the vehicle, and I am going to choose pixel labeling. Okay, this is the first week which is great. Let's say one more level. Just I am going to road. This will be a road, and again pixel labeling. So just showing you multiple we can label it. Just I will select the vehicle and I will start the labeling like this. And we can say that this is the vehicle, and you see that is showing this color, right? Same way we can vehicle this. Now if I have to label the road, just simply I will select this area from here, and I can say this is something road. Here I can connect like this, and you see that this is labeled as a road. And there is an option for flood fill also. If somewhere is missing, just simply we can use this flood fill, and we can just simply move it like that. So it is, everything is filled here automatically based on this color. But there are some issues, so we if images are cleared, we can use these flood fills also to fill these things, because it's looking, pixel intensity values are looking same. That's why it's filling everything here. Okay, so like this we can label. So once you will label this, there is a option to automate all this process. Here is the option, select the algorithm and click the automate. It will be automate on all the images automatically, so you don't have to do manually. And then export all these images. Once you export these images, you will get original images will be exported like this, which I just showed you here, and another image will be this labeled one. So we require this labeled and original raw images to train our deep learning model. I'm going back here, and once we have that data, simply we write the algorithm deep learning model. So these are the some steps here. So I am going to use pre-trained model, because for such kind of application, race rate 50 pre-trained model is good. That is defined, that is not designed on the top of the MATLAB. Another platform is used, and I'm going to import. So what I want to show you, you can import other models also which are not on the top of the MATLAB, or you can design in MATLAB from the scratch also. And further, this is the image data store. So see, we are not going to read thousands of images at a time, because it will take a long time. Whatever folder name is there, this folder name, just we can provide it, and we can create a image data store. And here you see here, just simply if I type here IMDS, you see that we how many images do we have here? We have all the path of the images. We don't have labels yet. So this is a step by step which we process here, and I'm not going to execute because deep learning model takes time to create a model. It will take at least 2 to 3 hours if I train all this model. This is the first image from there which we are reading. Just a step I am going to show you, and what kind of label classes do we have based on the pixels: sky, building, poles, road, pavement, and all these things. And further, we create a pixel label data store, means the label data which we have. So, and we use label overlay command to show here based on the pixel value, I mean color value, what it shows the classes. Which color is the bicyclist, which is the pedestrian, which is the car, fence, all these things. Once we have this data, we just I am going to show you something here. We design the layer. In this case, we are using RaceNet 50. So we are just modifying the RaceNet 50, some part of the layer from there, like pixel classification layer. We are replacing the RaceNet 50, the RaceNet 50 which we have. So this is the RaceNet 50. Sorry, RaceNet 80 it was. Sorry, RaceNet 80. So you see that 71 layers are there, right? If I give this command, analyze network in A inside, it will show you all the layers of RaceNet 50. So because in RaceNet 50 maybe image size would be different. In my case, my image size are different. We require to modify that layers. Like we have to modify the input one and the classification layer. Because in classification layer we provide the number of classes. Maybe in RaceNet 18 there were different classes. In my case, maybe there are 10 classes or 5 classes only. Maybe in RaceNet 80 maybe 18 classes are there, right? So these are the layers showing you how these layers are connected here, and what are the learnables, what are the activations. Once I am happy with that, after modification of that transfer learning, we provide the training options, like what will be the initial learning rate, what will be the, like you see here, initial learning rate is 1 into 10 to the power minus 3. So as much as low this value is there, accuracy will be high, but it will be a cause of the overfitting also. We have to take care how many times full cycle it will run. So more you will see about neural network in the tomorrow session. Okay, once we have all this, just simply we use this function to train network. These are my data stored. This is the layers, and this is the options where we provided what will be a solver, what will be a initial learning rate. Once it is trained, I will have this trained model as a NAT. Then further we use semantic this one. So let me I am not going to train it. I am going to just load that trained model, but still it will take time because I don't have a supported GPU actually. So what I am going to do, just I am going to read one image. Now model is trained. If I train it from again, then it will take long time. Okay, I am getting the error. The reason is that I haven't created this data set. Just I am showing you. Just leave this part. So further, once we have this model, we use this function to predict the C value. And what is the C value? That is the label pixel intensity value. Okay, and then by using this command, we can show that images here. Like it is not showing here because I am not going to execute. It will be like this. Okay, all images are removed from here. Just wait a minute. I'm just going to open this again. So the workflow is like that. Create the image data store. After using that, after labeling the data, once it is labeled, then we create the layers option. Then we train it. Once model is trained, like this it will be shown here. We use this. We got this pixel intensity matrix and overlay on the original image, that is I, and this is the predicted one. So based on that, it will classify and it will be shown here. So once model is trained, we don't have to do anything manually, and I can use that model for the perception. Okay, I am switching here. What is reinforcement learning? For the lots of applications are there on walking robot using reinforcement learning. How it work? Let me explain that. So we have a reinforcement learning toolbox available in MATLAB. How it work? You can use that reinforcement learning as well. So what are the basic elements of the reinforcement learning? It is the advanced, we use the deep learning for the policy. So okay, what elements will be there? Agent will be there, policy will be there, and this will be the algorithm to train this model, and there will be some rewards and environment. So agent will, in policies, some decisions are taken, agent has to select this is everything automatic. So agent will first watch the environment. Based on the environment, he will take some decisions from the policy. If the agent is taking the correct decision based on the environment, then he will be rewarded. Otherwise, he will be rewarded as a negatively or positively. If he is taking the correct decision, he will be rewarded positively, else he will be rewarded negatively. So agent will know, okay, I am taking the wrong decision, it means I am not getting the good reward. So he will always try to take a good decision. In the example of that robot walking which I was showing you, that animation, he will learn, okay, I am not getting the good reward, so I have to again I have to try, and if I am going on the right way, then I am positively rewarded. So agent will learn automatically. In our case, the agent is what? That walking robot. So for one example, very simple example I am showing you. If you have a parrot, let's say that I want this parrot will follow this some walking stair. I want that parent will walk through the stair and it will go on this swing. If parrot is following the stair and going on this swing, I am rewarding with some leaps. Parrot is happy. But if parrot is going on the swing, but he is not following this stair, I am not going to give him this green leaves. So parrot will think, okay, yeah, if I go through this on the swing through stair, then I am getting the leaves. The parent will learn to learn through stair to go on this swing because he is rewarded. So he will have he will have this kind of application. It will be installed in his mind that okay, if I go through that, then always I will be rewarded. So that's a self-learning kind of things. So here human is training and their reinforcement is training. That's model. That's all. Okay. One demo I am going to show you of robotics toolbox. Plan a reaching trajectory with a multiple kinematic constant. This is a simple demo. You can use robotics toolbox to design your model. So just I am going in the help. I am going to show you something how you are going to start robotics toolbox. So robotics toolbox is used to design a robot virtually. Okay, or you can interface some other robot vendors. If you have, you can interface with that also. So just I'm going to click, and how you are going to start the robotics toolbox. So simply that is a part of our robotic system toolbox. I am going here in get started. First of all, we have to understand what kind of units are in robotics toolbox. It follows the MKS. Length will be in meter, time will be in second, angle will be radian. Everything is given within the MATLAB document. Okay. Second is rigid body tree robot model. So what is the rigid body? What is the base? Rigid body is means which will be connected through base. Okay, that's the rigid body here. And further, if I go more below, there is a rigid body joint, means another body where we are going to join that. So there is a rigid body joint option available there. Once we have joined, then we connect another child bodies that are called child bodies. You see that from this rigid body one child body is connected. And to do this task, we have step-by-step functions available here. So if I scroll this above, build a robot step by step. So first of all, we created one rigid body. That's the base one, that is the parent. And further you see we have rigid body joint, we have added the revolute joint here, where what will be the position of that, everything is defined, right? The next step is to connect the another is it's showing how it looks like. Okay, the next step is how we are going to connect another one. So now you see that again rigid body, body 2, and what will be the joint for that step by step. So second body is connected, same way you can connect multiple body 1, body 2, body 3, body 4, and the joints for that, and what will be the place of the joint in the Cartesian. And once we have done this multiple, you can join like this, and you can provide some kind of dynamics kinematics to move this complete robot. So you are going to learn from there. From this you can learn that step by step. Okay. So just let me move here again. This demo is basically which I am going to show you what I have to do path planning for this robot arm. That by initially robot is in this position here somewhere. I have to show the robot that they have to follow this path, and it has to become to catch this cup. So set up the robot model. So see, this is not a 1 hour or 2 hour process to do these things. You have to know all the kinematics. You have to know the waypoints, how it is coming here. And once we have designed this, we have to solve this using the optimization. There are different optimization algorithms to solve such kind of things. So set up the robot model, define the planning problem. These are the workflow of that. Create constraints objects, find a configuration that point at the curve, means where it has to be moved, create and visualize the generated trajectory. So this is a trajectory, is a simple 3D plot. And if I move here, so this is still opening. Just wait a minute, it's taking time to open. Again we are importing from CAD model. Import robot, here is the option here, what is the data format, and you can design it in the MATLAB using the Simscape Multibody if you have to design the mechanics of that. I am not going to here. Now you see what will be the curve height, curve radius, curve position. Once you know, just provide all these things, then add the rigid body for the curve it is. So two things we have, one we have a robot arm, and we have the curve. So once we have, then we define the planning problems there. Start in the home configuration, some changes in the robot configurations, where from where gripping will start, that position you can have to define. Number of waypoints means xy coordinate of that path here which I was showing you here. This path, that's called the waypoint, how it is going here. So this is not this waypoint is just a random waypoint which we are generating. Once this waypoint is generated, here something which I wanted to show here. Here GIK solver is used to solve this, to achieve this position which I was showing you. So it will move like this and it will come to this point. Okay, let me run this and just simply show you this animated robot arm. So what I want to say, this kind of 3D models, if you want to design, you can use Robotics toolbox in MATLAB. And to design that mechanics of that and chassis of the robot, you can use Simscape Multibody, or you can import from the CAD model as well. And you see lots of lines are there to do these stuff. That's why I'm saying lots of expertise required to design even a single manipulator. If I am talking, it is what? It is nothing, it is just a manipulator robot. And you see this perfectly, it is following that path. Once it will come in this position, then it will move forward to go it. And you need not to worry if you don't have a background of robots. You can use the documentation of MATLAB, as I showed you how to connect everything, rigid body and joints and all these things, and childrens of the parents. So everything is given step by step. I will suggest that follow that steps to design these models if you want, if you want to work on that robotics. So once I am happy with that, if my verifications are done, testings are done, then we can go for the hardware part modeling, right? And the controller which is used, either here no controller is used, here it is an open loop. So that's why we use the solver to solve this. Instead of this, we can use some kind of PID and controller. For that, we require this exact data, how this will be moved. We can give it as a reference, and at the output we can check it is following the same path or not. That's the easiest way to do that. So here it is animated, showing it moved like this, then here, from here to here, right? Okay, some other toolboxes which can be helpful for you to design. Robotic System Toolbox. Robotic System Toolbox provide tools and algorithms for designing, simulating and testing manipulators, mobile robots, and you can design a complete humanoid robots as well using Robotic System Toolbox. For manipulators and humanoid robots, the toolbox includes algorithms for collision checking, trajectory generation, the waypoints which I was talking about, forward and inverse kinematics, and dynamics using a rigid body tree representation, which I was showing you how you will get the help from the help one. For mobile robots, it includes algorithms for mapping, means of course you require a map how your robot is going to move, localization, path planning, path following and motion control. Lots of examples are there, but if I run it will take long time to execute. That's why I'm not going to run. And in some cases ROS is used, robot operating system, which we require to install that. So if I go here in robotic system toolbox, and if I go in the examples, you will see some examples are given here. Lots of examples are given. Track a car like robot using the particle filter, different kind of filter. It is star, how it can be tracked. Okay, then you see there are lots of examples are given there. The example which I demo which I run, this one, it was this one, right? You can design a control this kind of robots also, like this is a manipulator kind of things. It will just take this from here, that's a manipulator. Okay, here some examples are given. You can use these examples for your reference. And this is the path planning, how to do. So in this case we require a ROS also. This is the path. You can design this kind of figures also here, and you can just how your robot will follow the path, what will be the optimized path to reach from here to here, that kind of things. Means you can optimize and you can show that also. So this is the path after the execution. And more complex, if he has to visit from here to here, then what will be the optimized part. So again here optimization is used, that's the open loop, and here optimization is used to solve. So first we require to create a problem, then we require a optimization to optimize that. Advanced optimization if you want to use, so we have a global optimization toolbox in MATLAB available. You can use that for optimization purpose. ROS toolbox. For ROS toolbox, we require you require a ROS software that is free. You can install it and you can interface with the MATLAB. So it supports version ROS version also, ROS 2. So ROS is just a set of programming how you are going to interface and how they can communicate. So networking things are also written there in that program. So ROS toolbox provides an interface connecting MATLAB and Simulink with the robot operating systems, enabling you to create a network of ROS nodes. The toolbox includes MATLAB functions and Simulink blocks to import, analyze, and play back ROS data recorded in ROSBAC files. So ROSBAC file is a file extension where these data are saved. You can also connect to a live ROS network, means let's say if you have real time of robots and if you are connect that with that. So two ways you can use the ROS message, two ways data are received and transmit using this. The toolbox lets you verify ROS nodes via desktop simulation, and not only this, you can interface gazebo also. So what you can do with the ROS, it works, this is the architecture like this. So ROS is nothing, just a networking message service based. So here this is the our all analysis are done in the MATLAB, and we are interfacing with ROS. ROS is the way how we are interfacing the real time robots, and from here we are controlling that. Once we are happy, this is the testing how we can do, how we can connect through software. Not only MATLAB, different softwares you can also use. How data, these are the data exchange paradigm, like ROS nodes is there. One is publish and subscription based, another is that ROS nodes will send some request, and then ROS node, this service, it will give some response to the client, server client based kind of connection also you can use here. More, how to get help. So let me open that mathworks.in and videos. That's the link from where you can get the help regarding robotics. So I am going to share this with you. You can use this link to get more help from mathworks website. Okay, here it is here. So here's the option that what kind of videos are you going to search. Let's say I am going for the robotics one, and all these webinars, recorded webinars and videos which you will see, that is based on the robotics. Okay, one thing more I wanted to show you about state flow. After this I will show you how state flow you can use for the controlling purpose. So here we have all these videos available based on the what is the robotic system, and some applications are there based on the robotics, and you want to see how industries are using MATLAB and Simulink, and you can use that for your reference. Just I will go in the newsroom, and from here just I will go okay, it's not given here, just wait a minute. These are the stories from different companies. So just one thing which I wanted to show here. Okay, this is the media coverage. Okay, somewhere it has to be here, user stories. Okay, so if I want to know some user stories based on the robotics, just simply I can search how industries are using to design robotic applications using MATLAB and Simulink. So these are the some which you see this user stories that are from industries, how they are using. And even not only industries, colleges also like IIT Delhi, they are using to design mechatronics kind of things, robotics kind of systems. They have a campus wide license, that is unlimited license. Every students can use, and every toolboxes they can use, they use there. Okay, I want to know that in any Indian company, let's say Tata is using or not, some user stories are available here or not. So you see that two user stories we got here from Tata. They use MATLAB and Simulink. Tata Motors develops engine management system for Tata Nano, the world's least expensive car. They use some part of Tata Nano applications using MATLAB and Simulink. Tata Motors European Technical Center accelerates development of autonomous vehicle control algorithms with model-based design. So lots of user stories are there. Here's the option you can refine by capability, then refine by product. Different options are there. Refined by industry, automotive, control, embedded, commercial, and government, how they are using. You can check it directly from here. Okay, if I go in the support in MATLAB, let's say if you want some help here, so we have videos available, apps are available, right? Some codes are available here. So there is a file exchange option also. You can visit on file exchange. This is a community from where you can search some ready-made codes from here, which are designed by other users. They use the MATLAB for that. So if I want to know something is available based on the robot or not in the file exchange, so robotics code files are available. Lots of ready-made codes are available from user defined. This kind of robotics playground extensions, you can go through that, you can download it and you can use for your reference. This kind of models are designed and codes are uploaded by other users also. I have my file exchange also. If you are interested on machine and deep learning in MATLAB, so I have machine learning model to predict diabetes, machine learning model to detect arrhythmia from ECG signals. These files I have uploaded here. If you have any issues, you can design a fuzzy logic system to save water in irrigation. So this here I have all codes available. So you can use this for your reference. If you have any issue, you can come back to me and I will reply you. You can mail me also. So like I have some algorithms which I have created, India COVID-19 patient forecasting model, and apps also I have created here, .exe file. Okay, so lots of things I have also uploaded. You can download it from here. Okay, the last thing I wanted to show you how state flow work, because it will be required in robotics and your problem will become very easy using that state flow. Just I'm going to close everything from here and I'm just switching. What is the state flow? Just let me show you what is the state flow which I'm talking about. The control system modeling, before the controller which we used to optimize the response of the system. But there are some other kind of controllers also. If I have to switch some system, let's say I want after some duration I want this subsystem will start, then this will start, some kind of controlling resetting, we use state flow. So state flow is used to model and simulate decision logic using state machines and flow charts. So this is like a if else condition kind of state flow. And the good thing is that we can generate the embedded C code to deploy in a controller of state flow. So what I'm going to do, very simple model I will show you, just how you can start with that. So I'm going to start here Simulink, and from the Simulink I am going to start from the basic model. Let's say here this is the library browser here, and I will go in the state flow. And here I have this state flow. I have to add the chart, that's all which we want right now. Just simply right click, add the chart, and the controller which we design inside the chart. Okay, and from here one thing more you have to do, what inputs and outputs will be there, what symbols, which kind of symbols are for the input, outputs and local data. Just click here, it will be visible here, that's all. The half-wave rectifier which I have designed before, that was based on the circuit, but I want to design a digital programming based half-wave rectifier. Let's say that I want to use a half-wave rectifier, and let's say some inputs I am giving to hardware, there is some kind of programs and it is converting as a half-wave rectifier. So how we can design that? First of all, we require from here chart that are called states. Okay, so I have two states here, like this it will be, and I am going to connect this like this. One is you see the one is arrow sign is in left side, one is in the right side. These are the called states, and these lines are called transitions. Okay, and here you have to provide the what is the state name. So let's say this state name is on and this is the state name is off. Fine. Now we have to provide some conditions. So what I am going to do here, conditions we provide in a square bracket on transition line. So I am going to provide x is greater than equal to 0, then it will come in this state. Okay, and another I am going to provide x is smaller than 0, then it will go in this state. Okay, if it is in this state, what execution I want? If it is in this state, what execution I want? I have to write it here. Just simply, first of all, what entry will be there? So you can write complete entry like this, or just simply en. And if it is in this state, that's the entry point, and duration during means during, if it is in this state, then what execution will be done till that time if it is in this state. So we use du, or you can use during as well. So I am just using du, and colon, I want y is equal to x. Y is the output and x is the input. Okay, now in this case, and I'm going to design the full wave rectifier. Entry and duration colon, I am going to provide y is equal to minus x. Perfect. So on off state, when x is greater than equal to 0, y will be x, and when x is smaller than 0, then y is equal to minus x. That's all. And here we have to define what is x and what is y. So in our case, x is input and y is output. Once we have designed this, let's verify that. And see, this controller is designed, I can deploy in a hardware. When we give some kind of sine wave, automatically it will convert in a full wave rectifier. So I'm going in the main model here. So now you see that we have an input and output also. So simply I am going to use the sine wave. So sine wave is here, sorry, not this sine wave. I want from source this one. I'm going to connect this, and also I want a scope to visualize this. Let's run this and check this. And check this. So this is a half wave rectifier, but is looking discrete, right? So again, what we can do, we can just decrease the time step from here. MATLAB is selecting automatically. So I want it looks like a continuous. Just simply I will just go in variable step, and let's say that maximum step size is 0.001. So what will happen? Multiple samples will be created in this case. So before, what was happening, let me explain you. Let's say that time step is 0.2, let's say. So whatever value it is getting at 0, it will hold till 0.2, then 0.4, then 0.6. That's why it looks like a discrete. Now I have decreased the time step, so multiple samples will be created, so it will looks like a continuous. See, and the perfect. Without using an electrical circuit, I am able to convert in a full wave rectifier. More, what we can do, let's say I have to create a square wave. Simply I will just remove this. I want entry, whatever value, when it is in this state, I want y will become 1, and when it is in this step, I don't want to execute continuous, just entry, it will hold the value, let's say 0. That's all I have to do. And if I go here, if I run this again, okay, there is some error here. Let me check where is the error. In both, I think it is one something it's showing here. Oh, sorry, I have to use the colon. I forgot that colon here because we are just enter. So it will hold this value if it is in this state, when x is greater than equal to 0, this input. When it is smaller than 0, then it will give me the value y, sorry, 0. So I'm going to run this again. So we can run it from directly from scope as well. So from here I'm going to run, and you see that we got the square wave, right? 1 0. So how to convert sine wave as a square wave? Very simple. And further, what we can do, we can deploy this controller there. Some advanced controller I have designed to control the fan through Arduino. Just simply I am going to show you how it works, but I'm not going to run because for that I require a Arduino actually. So cd Arduino. Simply I'm going to open that model. So this is a state flow where I have designed. So here you see in this case two fans are there, fan 1 and fan 2, and this both will run parallelly. Okay, so you see that if the I have a temperature sensor in my Arduino. You see here I have provided from pin number 14 Arduino. The temperature is going as an input. Based on the temperature, I want to select which fan will be on and which will be off. So you will be able to understand that if I am not using the state flow, this kind of controlling will be very difficult in the traditional way if I am designing. Now you see here, if temperature is smaller than 0, then fan will be off. If temperature is greater than equal to 0, then fan will be on. This is the on state. And one fan will be on. But if temperature is smaller than 2.50, this complete fan will be off. But now temperature is greater than equal to 1, one fan is on. But when temperature will increase more, let's say 2.5, then this both fan will be on. And here here the data is saved as a logical. If it is on, then the value of this state is 1. If this fan is on, the value of state is 1. So simply fan 1 dot on, fan 1 dot 2. If both fans are on, means the summation will become 2. Only one fan is on, then it will be 1. So this way we are getting this outputs. Two fans are on, we are adding 2 value will get, else we will get 1. And based on that we have this multi-port selector. So one fan is on, it will give me here some blinking here, red or green. One fan is on, then green will be on. If the value is 2, then second will be selected from here, and this will be lamp will be glow, right? So it is controlling through this. This is a selector. No fan is on, it will show here some value. Whatever control I want, I can add it here. For if first fan is on, then I have connected this lamp here, green will be glow. If second fan is on, both fan is on, then red will glow. Some control, let's say if I want to do, or let's say on the based on the threshold value of temperature, I want to control the fan. So we use state flow like this to design this. So this was the complete session for robotics workflow with MATLAB and Simulink. So if you have any query or questions, you can ask. For to designing an armed unmanned vehicles, we already discussed about that. So we have that toolbox. You can use UAV toolbox, provide tools, reference application for designing, simulating, testing and deploying unmanned aerial vehicle and drone applications. You can use all these things. The flight log analyzer app lets you interactively analyze 3D flight path, telemetry information and sensor. This is also a kind of UAV robot, so you can design this kind of robots also using UAV toolbox in MATLAB. That's all. If you have any questions, query, you can ask me. And apart from that, if you have any query, you can write me on email. Just I am typing my here my email.